So our next speaker, if you want to move the slide, is Dr. Taylor Uekert, a research analyst at the National Renewable Energy Laboratory, NREL. Her work focuses on understanding the environmental and economic impacts of circular economy strategies in the plastic, food, chemicals, and clean hydrogen sectors. Prior to joining NREL, Taylor received her PhD in chemistry from the University of Cambridge in 2021 for her study of solar-driven conversion of plastic waste into hydrogen fuel. In her spare time, Taylor also runs the Green Score podcast, which provides simple tips for everyday sustainable living.
Awesome. Thanks so much for that intro. Let me get my screen shared. Okay. So first off, I apologize if I am not speaking as clearly as you would like. I went to the dentist this morning and my mouth is still numb. So always a struggle. So yeah, today I'm going to be kind of tagging onto Phil's fantastic talk. At the very end, he mentioned how LCA can help guide research, and I'm going to focus on that topic a little bit more. And just a kind of disclaimer here, this is, while I do a lot of LCA in my day job at NREL, this is not related to my actual NREL responsibilities. Science communication is something I'm really passionate about, so it's something that I do in my spare time. All right, so let's kick off with a little bit about what is LCA and why is it important. Again, Phil introduced this already really, really well. But life cycle assessment, or LCA, is really just the analysis of the impact that an object or a process has on the world around it. This can encompass a lot of different environmental impacts, ranging from the ones you hear about most often, global warming potential or greenhouse gas emissions, all the way to things like acidification, eutrophication, land use, water use, all that jazz. Now, the really important thing about LCA is it can be helpful for making decisions around what you should be prioritizing in order to reach sustainability goals, right? And this can start all the way from really big scales. Governments use LCA in order to guide policy decisions related to sustainability. If you come in a little bit more, companies, which have been one of like the huge users of LCA traditionally, they might use it for complying with environmental regulations. They might use LCA to figure out where are the issues in their supply chain and how can they improve that in order to kind of have a greener supply chain going forward. They might also use it in marketing. I'm sure you've seen some products that say like the carbon footprint of this milk is, I don't know, however many kilograms per liter. Always, take those with a little bit of grain of salt, but that's a really common use of LCA in industry as well. And then if we kind of come in a level further to researchers, there's a lot that we can do with LCA as well. We could benchmark new processes. Say you've come up with a new synthesis and you want to say, how does it compare to the previous existing one? You can identify areas for improvement. So say in that synthesis, you figure out one solvent is particularly problematic. Could you then figure out how to replace it? And lastly, it can really help place your technology within context. So it's like, how much of a difference on a larger scale would this innovation make? Is it like a drop in the bucket of meeting climate change goals, or is it actually going to have a huge effect? Now, given the importance of LCA, I do think it's kind of interesting to look at where LCA is taught right now. So the Forum for Sustainability Through Lifecycle Innovation conducted this global survey of over 100 universities in 2022, and they asked whether they were teaching LCA courses, and if so, what was kind of the major that they were teaching that in. And you can see here the vast majority, so over 50% of LCA courses were being taught in engineering programs, chemical engineering, process engineering, environmental engineering, and so on. You also have, a solid chunk of the pie that's going towards environmental and sustainability studies, which you would kind of expect, as well as architecture and business. But what you might notice is missing from this is any of like the standard physical science degrees, chemistry, physics, material science. I did nanotechnology, which is like a fancy version of material science. Definitely wasn't offered there either. So why should this bother us, and why should we think about how we can teach LCA to physical scientists? Well, I think there's a lot of reasons. So if we think about the development of the technology in terms of technology readiness levels, or TRLs, you start from lab scale innovation. That's like the 1 to 3 on this scale that I'm showing. You can then go to upscaling, which is like the 3 to 6, and then you go to deployment, which is more the 6 to 9. And traditionally where LCA has sat is kind of more the upscaling and deployment side of things once you already have a lot of data about your technology. And that's good. It means you can do more rigorous life cycle assessment. You can make sure all the details in there, you're going to have low uncertainty of your values. But I would argue that it's also important to be doing it at that really early stage. Even if it's not going to be as detailed, it can serve as kind of a basic sanity check LCA. Like, am I pursuing the right thing? Is there something else I should be considering? And basically, if you do consider LCA early on in this innovation process, I think it can enable you to make more sustainability-oriented decisions in your research. And it's going to help you avoid any unexpected environmental burdens that pop up later on that will then actually probably be harder to mitigate than if you had kind of fixed them at the very beginning of this process. From a kind of more personal perspective, understanding LCA can really help you think critically about, maybe it's your own research topic, maybe it's others, maybe it's even just your everyday life, like looking again at that packaging and being like, does this number make sense on this milk carton? And there's also really an increasing demand for LCA expertise in both industry and academia. And one thing that's interesting is most of the existing expertise, again, it comes from those engineering backgrounds. And so there's sometimes a little bit of a disconnect between this early stage physical science research and the LCA experts. So kind of bridging that gap, you're going to fill some unique expertise there, and that makes you a value both in industry and academia. All of this being said, lots of benefits here, but there's also a lot of challenges. Phil mentioned several of these in his presentation. So there's definitely some barriers to entry. There's confusing terminology. It took me a solid few months to understand LCA, because when I did grad school, no LCA experience. When I came to NREL, I'm like, I want to learn this. And, it's a steep learning curve to start with. Once you get used to it, it's fine. But again, terminology, tricky. Also issues with software. A lot of the existing LCA software is really expensive, and that can be prohibitive for a lot of researchers and educators. Data, Phil mentioned this, being able to find data for kind of early stage research can be really tricky. And the last one that I want to emphasize here is misinterpretation. So LCA is being called for a lot more in like grant proposals and things like that. And there has been some LCAs published where, people made a lot of simplifying assumptions because they're like, I need to do this for my grant. And then maybe their results weren't as accurate a reflection of reality as they could have been. So kind of addressing that misinterpretation issue is another challenge. Okay. So I'm going to just go through a couple snapshots of this pilot workshop that I conducted on life cycle assessment for nanoscientists specifically, to kind of give you an insight of how you could incorporate this into graduate studies and how it can be helpful for these budding researchers. So the audience here were some PhD students at University of Cambridge's Nano DTC. That's where I did grad school, so that's why they let me pilot this out on their students. The objective was really it was twofold. One was to provide sufficient understanding of LCA so that they could critically read the literature and think, does this make sense or not? And number two was to be able to do a really preliminary analysis of their own research so they could figure out, maybe how their technology stacks up against the incumbent or where they could improve going forward. And the way we structured this was 4 one-hour lectures based on the 4 steps of life cycle assessment. So that's starting with defining your goal and scope, so what you want to achieve with your LCA, building your life cycle inventory, so essentially finding those input and output material and energy flows, doing the actual impact assessment, and then interpreting the results of that LCA. And these 4 workshops were combined with demonstrations of OpenLCA, which is a open access free software for conducting LCA. I will caveat that we did have to pay for an eco-invent license, which is like the data that goes behind LCA to do all your calculations for you. So it wasn't completely free, but something we're working on going forward. And there were some optional assignments for the students to really practice using the software and kind of building their own life cycle inventories for their process. So I'll just go through kind of one slide per workshop. So the first one was introducing the LCA. This was really expectation setting. So what can and can't you accomplish with LCA? How can you use LCA, and how can you define what you're trying to accomplish with this? And this is just a couple examples of things that I wanted to highlight for the students where you could use these early stage LCAs to kind of design your experiments better. So should I be using solvent A or B? Something along those lines. Also for optimization, so figuring out which parts of your technology look bad and which you can improve. And then also for benchmarking, so comparing your innovation to the status quo. And I think an important part of this, in addition to what you can accomplish, was highlighting the limitations. So, I think we often look at LCAs and are like, oh, it's giving me a number. That must be the be all and end all number. But just like any type of science, there is uncertainty that goes into these calculations. And so just to be aware that there are ranges on all of those values, and to take everything with a little bit of a grain of salt. So session 2 was on translating your research into LCA and building your life cycle inventory. And I'll mention this is probably the most challenging part. It's basically the data gathering. And the reason this is particularly challenging for early stage research is there might not be any literature you can pull from, right? So you're probably going to have to be collecting all of this data from your own laboratory experiments. So we kind of broke it down into how you can break your process down into little boxes, and then for each of those boxes, figure out what your inputs and outputs are. How you can estimate those material flows, how you can estimate electricity use, heat use, all of the things that you're going to need to make your final product. And this is just a screenshot showing one example where we kind of drew out what we call a process flow diagram for this technology. And then we make an Excel sheet for each of those steps where we are able to calculate out our material and our energy flows. And then we talked a bit about how you would input this into an LCA software using eco-invent background data, as well as what to do if eco-invent doesn't have any of the data you need. This often happens. Say you're working with a new type of catalyst, you might have to be like, okay, I'm just going to approximate it by the most important metal rather than trying to find the exact material. All right. And then session 3, probably the most technical part, and this is really just conducting the impact assessment. So we talk about how the different methods that are available for LCA work, how they do that multiplication, because it can be a little bit different depending on your method, how you can choose metrics, because there's a lot of them out there and it can be tricky to know what's important for your research. So this is just kind of an example where we showed where these different metrics are coming from. So for example, acidification, if you're emitting NOx or ammonia or sulfuric oxide, sulfur dioxide, you're going to get a change in your soil pH, and that's kind of where that metric is coming from. We also talked about how you can conduct LCA without software. So there are lists of some of these kind of conversion factors out there, especially for global warming potential, not necessarily for all of the impact categories. So that could be a great kind of option if you don't have access to any sort of software. And then we also touch on ways to strengthen your life cycle assessment. So hotspot analysis is figuring out which material or energy in your process is most impactful. You have sensitivity analysis to explore kind of if your yield, for example, changed from 20% to 40%, how that would affect your process. Also multi-criteria decision analysis, which I think is really important here. Multi-criteria decision analysis just lets you combine a bunch of metrics into a single score. And that way, if you have trade-offs, you can kind of still see an overarching winner without being like, oh, but I don't even know how to value this process that is better here and worse here. And then the very last session was, I'd say, arguably the most important part, which is translating your LCA back into the lab. So this is essentially understanding your LCA results and figuring out how you can use them to make choices or improve your experiments. And one example I gave here, this is a real example from one of my colleagues. She wanted to know which process she should pursue. She'd basically come up with this new method for making a nanoparticle emulsion. It used some cool chemistry, and she's like, I have a lot of control, but I don't know if it's actually any better than just heating it up. And so we ran some numbers for her, and it turns out her chemical emulsion process was actually better across pretty much all of these metrics. And then kind of last thing was how to communicate your LCA to both experts and to the general public. And some key takeaways. Those ones for me were LCA does not necessarily equal the absolute truth. It's a very important tool, but do not treat it as like the Bible. LCA is also useful at all research stages, right? It can be used even at that early stage, and you can do it effectively with a little bit of legwork. And lastly, when in doubt, break LCA into manageable sections. It can feel overwhelming when you're first looking at all the information you have to pull together. But if you break it down into chunks, I think it becomes much more doable, and you'll realize how powerful it can be. So just a couple kind of concluding points. Overall, this had pretty good feedback, I would say. Everyone seemed to learn things that they thought would be useful in their research or their career, and they kind of had the tools that they needed in order to either look at LCA more comfortably or conduct it by themselves. And we're going to do another iteration of this, going to be kind of improving a few things next summer. And then I am hoping to create a publicly available online version at some point, but that's TBD, depending on timing. And yeah, I just want to kind of leave us with the thought of how can we make sure we're really strengthening this important connection between physical sciences and life cycle assessment. And with that, thank you very much.
Thank you, Dr. Uekert. And thank you for such an amazing talk as well. We loved your slides. I don't know if you had a chance to look at the chat. We loved the little drawings, and it made it really personal. And thank you for also letting us know of how to like apply it to our research. It made it a little bit more feasible, because I feel like whenever I think about LCA, it's like very overwhelming. But if we break it down, it definitely makes it easier. So thank you. So now we're going to move on to our breakout rooms. So there'll be a breakout room for Dr. Jessup, one for Dr. Uekert, and then the Beyond Benign Higher Ed team. They'll have a breakout room, and And then we'll have one for the Green Chemistry Connections, where our team will be there if you have any questions or suggestions for how to improve these events in the future. So I think Chloe is going to set those up in a moment. Feel free to join them as you please and change in between them. Additionally, when you join these breakout rooms, please just introduce yourself, your name, your affiliation, and then we can get to the topic and have a great discussion about what we just learned and talked about. Hello, everyone. Welcome back from the breakout rooms. Hope you guys had an opportunity to talk to some new people. But before we wrap up the event, I just want to thank all of our sponsors who make this event possible, that are listed here, and specifically to Sigma, who is one of our main sponsors for today. So that's all from us. But what we'll do now is just open up the floor. So if you have any questions that you would like to ask the team in general or a specific person, feel free to do so. Otherwise, we'll see you guys at the December Connections for the Latinx chemistry presentations. So thank you guys.